Abstract algebra is one of the courses that sounds the least applicable. I mean, by definition, an abstract course. But this actually turns out to be the basis of modern cryptography and cryptanalysis, and in one sense underlies a lot of stuff you've done in other courses. But that really means we're going to take the specifics away and start abstracting. That means we're going to take ideas and look at the broader and broader and broader context. But this is something you've done. You start with a number, counting, right? You start with things. I have 4 apples. Remember this in kindergarten? But then eventually you have 4. Separate from things, right? All of a sudden, numbers in and of themselves have actions and operations and things we can do to them. Then you get to algebra, and you have a box that contains a number I don't know yet, a variable. And variables have operations and things we do and ways we can combine them. And then the properties of those we get into examine. And as we change each new layer of abstraction, we learn more about the structures underneath what's going on. That's the purpose of this course. And to that end, it's going to sound really theoretical for quite a while. I promise there's a lot of good concrete work under this. 99% of this is you've seen before. I changed my office hours Monday, Wednesday, Friday, 12:30 to 1:30, Tuesday afternoon, Thursday afternoon. All of it's over in the Enrichment Center. Come bug me. We're going to go through a whole lot. Fraley and Brand, 8th edition. There is a recommended book. Actually, not the recommended book. I brought the wrong one. Number 3 book. We'll see that as well. A Shams outline for this course exists. There's a lot of solved examples in the Shams outline. I think it's like $20. It's a worthwhile purchase. It's got a lot of additional examples above and beyond what we'll see here. It's available in a lot of places. I know the bookstore has some. You can add to your bundle. This is a majors course, so here's where we're going to do stuff, and here's the stuff we're going to do, and when we're going to do it. COVID protocol. The university's not doing free testing anymore. If you get sick, I hope you'll get better quickly. I'm doing the recording I did last year. I've had some sound issues again, so I can't guarantee audio fidelity on this. I will post all of my written notes, but ideally, be here, it helps. Be here, it helps. I have stories. Oh, plus, trust me. I'm teaching a stats course for the first time, and I actually got to say it's correlative but not causative. But coming to class is correlated with good grades, I promise. Every section will have a homework assignment. There's a complete list of problems to be turned in for each section. They are due 2 days, 2 class periods after we finish section. If I get through section 0 today, that's due next Tuesday. The course calendar and the assignments linked to it through Canvas are all dated, and all the dates are on there. If that changes, I will change and update everything on Canvas. This is a course where I doubt we'll have a tutor. To that end, you should be coming to talk to me a lot. Get through and get assistance and figure out where these pieces don't quite mesh yet. We have 3 exams, 2 chapter exams. I think it's 0 through 6, 7 through 17. There's some skipping in the middle there. Don't panic. They're not the same number of chapters. And then a comprehensive final. Please try and take all the exams. They're weighted very heavily, and that means that if you miss one and try and double up, one exam becomes 40 or more % of your grade. I don't want to do that to you. That's a pain. But notice that homework is a larger percentage of the grade here than in several of my other classes, because again, this is a think about it abstracted class, and that means that they're going to be very different kinds of homework problems. It isn't run 17 calculations. It's explain. It's not truly proof in a lot of cases. this course does do quite a bit of proof-like work. Our emergency egress is right here, straight out, straight down across. If you've got large bags, tuck them in behind your chairs. Try not to obstruct the aisle in case you have to get out of here in a hurry. I don't want you to trip with anything. You'll get starfish updates. I prefer to work via email. Send me email if you've got questions. Guaranteed response within 24 hours. There is a complete schedule for this course. That's the homework list. That's the course schedule. Shows you everything we're going to do every day. So please notice there are review days built in a week before the exam. If the class doesn't otherwise have a question and answer period, again, I expect you guys to bring questions to my office hours as often as possible. And our final is unfortunately at 8 in the morning. I didn't write the final exam schedule, and I get with this every year, so we deal with it. No extra credit assignments, but there will be extra credit problems occasionally. If I'm rambling, it's because somebody's looking at me like, huh? And I'm going to keep going until that face goes away. Make sure your valid email address is in Canvas and Griffin Gate. If you're forwarding to another email address, that's fine, but I will send stuff out by default to those email addresses. Make sure your phone is on silent or vibrate. Last year I said that within 5 seconds somebody's phone rang, so I check every year. I'm asking for 75 minutes of time. I know it's not necessarily easy, but I think we can do it. Don't use tobacco in the classroom. We recently redid some of the flooring. This room hasn't gotten done, but you should go look at 333 next door. If you had class with me in there, oh my God, they changed the entire room. It's miraculous. I took this course in 1989. And this course was one of the reasons I switched from being a pharmaceutical physical chemist to a mathematician. This course changed the way I see math a lot. And I love some of the stuff we're going to cover. That end, I think this is cool. And we'll do this because it's fun. That makes me the sickest mother in the room. But that means to your end, I'm enthusiastic about this, and that gets me faster. You need to slow me down. I really need you to help me, not just steamroll through this, because I like it. Title IX. I am a mandatory Title IX reporter. If you disclose something to me, if I observe something, I am required to report harassment of any type, sexual, racial, gender, whatever it is, I am required to report that up the chain to our civil rights coordinator. If you would prefer to speak to someone who is not a mandatory requirement, a reporter, these numbers are available to you. Those are people excluded from mandatory reporting. You can talk to me about anything you want. Just understand that these things have to be reported to our civil rights coordinator. If you are legally entitled to accommodations, note takers, extended time for exams, etc., I need to go through the Office of Student Services up on 5th Admin, and they will send me a form that says this is what I am legally required to provide to you, and we'll make it happen. You don't have to tell me why, we just have to figure out what it is. If I could figure out how to do a matrix trick and upload this to the back of your brain, we'd be done at the home and have a beer. It hasn't worked yet. I can't watch your eyes flutter and you'll know Kung Fu, but this is where I say with a straight face, you have to be willing to push yourself as much as you can in this course. Because this is different. It's not the same sort of calculative course that calculus was. It's not an algebra course. It's a lot more thinking about how this works. Your engagement is necessary. I am 100% sure you can find every single question I'm going to ask you online. So far, I've found my exams online 3 times. I've taken them down from Chegg repeatedly. It happens. I mean, I keep giving you guys answer keys. They keep showing up online. Somebody's doing it. I don't know who it is, but there you go. That's a problem in one way. It's completely understandable in another way. But I guarantee you, if all you've done is look stuff up when you get to the exams, that's going to suit. I want you all to be working together on the homework wherever possible. To that end, if you're going to miss a day and need to send me your homework, that's the same scanning software I've used in the past. That page is on our Canvas page in the first module. Feel free to download that and use it to put your homework into a single PDF and email it to me. What questions do you have for me about the way this class is going to work?
When you say it's new, like what exactly do you mean, like a different type of math?
Well, a lot of this is really, I mean, the idea of the statement being abstract is really the key to this course. A lot of what I'm going to talk about starts the same way discrete started, with a definition and properties, and then how do we proceed from those. And so to that end, it's not, here's an integral, here's a derivative rule. Now let's do 100 of them so you remember how to do it. That's my new definition of different here. I think to that end, we'll find that a lot of this course is familiar in one sense, because we'll see concepts we saw in discrete, concepts we saw in linear, concepts we see in lots of other courses come back. Stuff we saw in Calc 2 and Calc 3. But it's not, we're going to do 1,300 Laplace transforms so you understand how to do it. I want to do that.
I heard somebody describe the content of this course as game-like sometimes. Like you're almost working out the rules of little games and then trying to figure out where they go.
Yes, but in one sense, that's actually the definition of all of math.
True.
Because in one sense, realistically, and there's a very famous quote, God gave us the natural numbers, the rest is the work of man. When you start counting, it's 1, 2, 3. Those we know, those are things. Everything else we made up to abstract from that, to build those layers. And so when I say, yeah, it's a game, we made up the rules and now we have to try and figure out, are we still following them? What happens if I change it? Well, we get a new game. How's that one going to work? Is it a game worth pursuing? And that means, realistically, yes. I'm going to throw rules at you and you're going to say, well, does this follow those rules or does this not obey those rules? But those are the same sorts of ideas we did when we talked about formal logic. We talked about sets, when we talked about the rules for modular arithmetic. All of those things came from stuff we know, but we're tweaking it just a little. Make sense? Mm-hmm. All right. Well, with that in mind, I would like to say that I'm going to dive right in. And it really means that I have to start with defining the things we're going to work with. So the first section of the text is, in one sense, review. In another sense, it's an introductory set of concepts. Every definition in a field of study starts with base concepts we don't actually define. You taking a geometry course here or just in high school? Anybody taking the geometry course here? Didn't think so. So there is no definition for a point. There is no definition for a line. There are properties, but we assume everybody understands this is what a point is, this is what a line is, this is what a plane is, and everything we put in geometry descends from those three ideas and our ability to do logic on them. So my fundamental concept here is a set. So what's a set? We did this in discrete, chapter 2. So it's been, you've seen it. A set is a collection of things. Sets contain elements. And element in this case could mean a number, an object, a function. We have sets containing lots of different types of things. I will say there is a unique, look, I'm going back to use the notation from discrete, there exists a unique empty set, which I will either write as the lowercase Greek phi or an empty set of braces.
Go over that one more time.
There exists a unique, that backwards E is our existential quantifier. The exclamation point means there's one and only one. There's a set that holds nothing. So that when I say a set is a collection of elements, here, these are all my Olympic gold medals. That's a set, right? There's nothing in it. But there's only one possible empty set. So my collection of Olympic gold medals is probably the same as your collection of Olympic gold medals, probably. It's the same as my collection of Super Bowl rings, right? But there's only one set that contains nothing. That's the same set, no matter what descriptor we're using to put on it. But if I have a set, I could describe it by what's in it. This is a description of the set of students in the course SMA310 Fall 2024 semester. That's y'all. I could explicitly list this set, right? I could write down all of your names. And this is the set, right here. Ta-da! But that means I've built this set from a descriptive rule or by explicit listing. This is called set builder notation. We see this a lot when we write the set of numbers so that, and then some property about those numbers. So this is a set of numbers, right? Or we could say the set of points that obey a particular rule. And then while the first set is finite, the second set is infinite. Now, there are some assumptions to be made in both of those. The first, that I'm talking about real numbers. The second, that I'm talking about ordered pairs of real numbers, right? So these sets live within some defined universe of discourse, assumed or somewhere in our set need to be explicitly mentioned. So I could equally write this second set where that R squared is the set of ordered pairs of real numbers. Questions so far? Familiar concepts, even if you have to really dig out your discrete book and go, I know I saw this once, man. A set must be well defined. What's it mean to be well defined?
does it mean to have a like bounds of some kind?
Um,
Try my best to remember.
that's not a requirement because it depends on what our set is a set of, right? If I talk about a set of people, I'm not gonna bind my people, am I? So I'm not quite sure how I would do that. I'll cast circles and spells. No, wrong kind of binding, never mind. I think it's got to do more, I believe, with this sort of idea here, with the way I describe my set. So what does it mean to be well-defined in that context?
I was gonna say, does it have to follow some sort of rule or like some sort of like fit in some sort of category?
Kind of, but then it's a matter of precision, then.
So non-infinite.
I like infinite sets. I mean, this set down here, this second set is infinite. Okay?
I was gonna say just finite, so infinite as well.
Right, but infinite sets are things I like, right? The set of real numbers is definitely infinite. Uncountably infinite. Remember that argument on cardinality? I have a set for you. The set of real numbers that are close to 1. Why are you laughing?
I see your argument. It's like, what is the actual definition of close to one?
I need to be able to look at an object and know, is it in my set or not? And if the terms are too fuzzy, then I'm kind of there. And I don't want to do that. I want to be clear and precise as best I can. So a well-defined set has a defined membership requirement. It could be a bound in some fashion. I want numbers between here and here. I want numbers whose distance from a point is 3. So that's a circle, right? It's a clear, this point is on the circle, this point isn't. I want to be able to say, this person is in the class or they aren't. That's why I was specific enough to actually put fall 2024 here. Because this is like the 11th time I've taught this course, if not more. I have a whole lot of students who have been in this course, but there are only you here now. And close to 1 is even worse than you might imagine. Because how do you define distance in numbers? Two is close to 1, right? But 100 is further away. Maybe. 2 has a very different digit in it. 100 doesn't. 1's in 100, isn't it? Ooh. How do you find close? I don't like it. That does lead me to a problem. You know, I can define a set and then still be unable to tell you whether or not things are in it. Now, this is a set I can actually define. And I can tell you very clearly whether or not a book is in this set. Yes? If I open our textbook, and somewhere in this textbook it says back on page 32, or back on page chapter 1, or as we will see in chapter 8, then that book is referring to itself. Yes? If I pick up my copy of Harry Potter and the Sorcerer's Stone, and it says, if you saw back in chapter 2, somebody picked up and broke the fourth wall, right? Interestingly enough, the Three Musketeers is in that set. The actual book, The Three Musketeers, was published as a weekly serial. And so it actually says, as we saw in the last episode, a couple of different times in the book. Great. I can look at a book and tell you whether it's in there or not. That means there's another set. Yes? the complementary set, books that don't refer to themselves. And we've already named a book that's in that list. What book did I name that's in that list? Harry Potter, right? I'm pretty sure most fiction novels are in that group. I'm pretty sure most biographies are in that group. I'm pretty sure most narrative books are in that group. But that's not a small group, is it? A lot of books that don't refer to themselves. I'm going to be bored and pedantic. I go down to the Library of Congress, and I break the entire Library of Congress into those two sets. I write down all of these books. I have a file on my computer now that are all the books in this set. And because I'm on the government's dime, I print it out. Big ass stack of paper. You can't carry around a loose stack of paper like that. Let's bind it. I have a book. What is the title of this book? Books that do not refer to themselves. But the name of this book does not appear in this book, does it? Which means it should be in the book. But then the book would refer to itself, so it's not allowed to be in the book. Bertrand Russell, one of the originators of set theory ideas, said this is a problem with the idea of a set and then sets of sets. And he called them classes and levels. And he said there are some ideas in sets we simply can't tell. And if we write a set like that, that's not well defined, because you can produce an item that you can't tell whether it's in or out. And if it's in, then it shouldn't be, and if it's out, then it should be. So our idea of a well-defined set is one that doesn't violate this idea. And that's kind of weird to think about to start with. But it is important to the overarching behavior where we say, hey, I'm not forcing you to write everything out. You don't have to have an explicit listing. You have to be able to tell if I give you something in the category, does it belong in your set or doesn't it? 99.9% of the time, we will be explicitly clear about what our set is, and we won't run into this sort of bullcrap. But verifying that our condition makes sense, that our membership criteria matters, and is allowing us to define our set well, is important. Questions? I know I'm hammering on this. It's going to become a footnote eventually. Yeah, is this set well defined? Yes, that makes sense to me. Off we go. We're going to define a lot of things. But again, here is another remember what this word means moment. What's a biconditional statement?
It means there are two criteria it has to meet to be true.
Almost. There are two criteria involved here.
Is that like the double arrow? Or like both ways?
It's our if and only if statement. I'm going to go back to geometry because it's an easy place to find a bunch of these. a square. What's the definition of a square?
4 sides.
Well, that's a quadrilateral, right?
Oh, yeah.
That's a square. That's not a square.
4 equal sides.
4 equal sides. What if it's tilted? You get a rhombus, right? Which is not a square, so there's more.
Equal sides with 90 degrees.
Equal sides and equal angles. So in one sense, my definition is I need to see 4 sides. They all have to have the same length, and all corners have to be right angles. If I show you a shape, and it's got 4 sides and they're all the same length, and each of the angles of the corners are 90 degrees, that's a square. If it's a square, then it has these criteria. If it meets these criteria, then it's a square. If and only if. Every definition is not just, we're going to call these things by this name. It's whenever I use this name, I mean these criteria. Later on, we'll talk about polynomials. Okay. You've seen polynomials since algebra class, right? What's a polynomial? There's got to be a formal definition somewhere, right? And we'll come up with one. And it involves, whole number powers, positive powers only, or 0 because we have a number without a power, like 2x plus 3, and there's got to be some variable in there that we're taking powers of. When I say the word polynomial, we're going to have a very specific definition. Part of my research work was investigating polynomials of a complex variable. And I was very specific. I was looking at the definitions. I was working my way through this. And I asked a question in an online forum. And I got back some amazing examples using 1 over z. And I said, that's great, but that's not a polynomial. And I kid you not, the gentleman to whom I had responded says it is by my definition. And I do not trust another word out of his mouth for the rest of his life, because he was disagreeing with every other math book on the face of the planet. I said, okay, you're a crackpot, goodbye. If we define a term, then I want to see these properties associated to that term. If you want to use a different set of properties and use the same term, we're going to have a confusion, right? So we have to be precise in our language. Unfortunately, that makes us sound like pedantic assholes a lot. Not much I can do about it. But that's part of the reason that we spend a lot of time at the beginning of courses making sure everybody's on the same page, knowing the things we are talking about. More questions? I promise almost all of this is a discrete review, but it's been a long time. Yes, no?
I just have a question about what's the sign in between z signs after
That
z?
one? Element.
Element.
And that's a member of a set. Z is an element of. Remember, we said sets contain elements, right? So when I use this after Z, I want to tell you, oh, Z is not just a real number, Z is a complex number.
What's that last symbol?
That's our C, the complex numbers.
That's a C.
Just as we have that funky looking R for the real numbers, we're going to get a lot of funky looking letters. Matter of fact, these are all sets. Oh, I forgot one. Q. The extra lines on them are to indicate that we would write them in some sort of bold font. I don't have a bold pencil. And there's actually a font built into the textbook. You'll see it with these extra lines called Blackboard Bold. These are natural numbers, integers, positive, negative, and 0. Real numbers, complex numbers, rational. Okay, wait a minute. Z for integer? I'm cheating. The word is actually stolen from German. It's Zahlen, Zahlan for integer. And rational, well, that's quotients. Right? A rational number is like 1/2, 2/3, 7/23, A over B. So quotient there. Now, I could make subdivisions of this. We'll talk about that more in a second. Yes, Ian?
No, generally I know these go in order where like that they contain one another. Is the complex? Now I've never seen the set of complex numbers compared with regards to the rest of them. Does it fit exactly in that order as well?
No, Q should be here.
Okay.
But yes, every real number, let me write that, real, natural, complex. Complex numbers are the form a plus bi, where I squared is -1, where a and b are real. So if I use a plus 0i, that's a real number, but it's also a complex number. Gotcha. And yes, they're nested that way. But that means I have a relation, a subset idea, right? N is a subset of Z. And it's clearly not the same as Z, right? There are integers that are not natural numbers. -1 is in Z, but it's not in N. If I wasn't sure about the relationship between the sets, if I knew that A might be in, but it might also be equal to B, I'd put an extra line, like less than versus less than or equal to. So I have N, Z, Q, R, C in order of getting origin. There are other sets in between, other options and ways to do more sets. We'll see some of them as we go along. But R, C, Q, R, and C are very important sets in the long run. Sometimes we only want positive numbers. And then I might indicate that I only wanted the positive numbers, like saying, oh, Z plus, only use positive numbers, or R plus, or Q plus. I can't do that with C, because C has 2 parts to it. They both have to be positive. Is one positive good enough? I can't do that. I can say, let's exclude 0. Now, why would that come into play to be important? Well, remember when we're doing quotients in the first place, we make the comment that the denominator can't be 0 because you don't know how to divide by 0. Here is an interesting question. And again, it's going to depend on the book. Is 0 a natural number? You'll notice I didn't list n in either of these, did I? Some textbooks say n starts with 1, 1, 2, 3, 4, 5. Some textbooks say n starts with 0. So you're going to have to look in different books. The discrete book used n equals 0. The linear book didn't. So we got to be careful when we start looking at this. I don't have a dog in this fight. There are some people who are very, very emphatic that the natural numbers start at 1, and some people who are really, really emphatic that they start at 0. I don't care. make a decision and run with it. I believe this textbook does include it. Double check. It's in section 0. Any respect?
I was just gonna ask if there was like a prevailing.
Nope. There's a fight on that
one
everywhere.
community. I was gonna say, 'cause I've never heard one, it's always been one way or the other, never.
But the reasoning behind that is bizarre.
Mhm.
It depends on how you make the numbers. And that's a whole other ball of wax, how you make a number. Anyhow, again, I'm pulling most of this from the discrete chapters. We did relations. Chapter 9, sections 1, 3, and 5 in the discrete book talked about relations. Chapter 2, section 4 talked a little bit about it. We talked about relations. We talked about functions. But really, we define a relation as a subset of the Cartesian product of two sets. And that's the set of ordered pairs, where A is an A and B is an B. So when we define two things as equal, what we're really saying is, oh, the first thing in the ordered pair and the second thing in the ordered pair are the same thing. So if I define the relation whose symbol is given by this, well, to think of it as a set means we're really taking the diagonal line in A, the visual graph there, right? But again, this is just another way of thinking of the idea of being equal, something we've already defined, but we can define any sort of relation between sets. And then the question is, what are the properties that we get from that relation? I have an interesting relation for you. If you have an object in front of you that is a rectangle, pick it up, move it, any way you want, set it back on the table. First question, did the outline on the table change? Yours did, because you turned yours sideways, right? You had a rectangle, when you turn it sideways, it doesn't sit in the same box, does it? Yours did. Because you set it back down the same orientation. If I give you a square, that's my geometry idea, and ask you to pick it up, move it, and set it back down in the same orientation so that it fits the hole you picked it up out of. How many ways can you do that? Those are moves, right? Those moves can be the object in my set. What moves are equal? If I do these three moves one after the other, could I do that in one move? What one move would it be? Now I get to define an operation on moves, doing them one after the other. That's arithmetic. That's like adding, right? I do this, then I do this, then I do this. That's an operation. So I need to be able to define for any set I've got what equality is, what my operation is, and then I can work on that set and do things with it. Moves is going to be one of the examples we use. Look, chapter 7. A function is a relation. I should put some sort of serif, so you know capitals from lowercase. I don't have lines on my page. A function from one set to another is a type of relation where we say for every x in the set X, there exists at most one y in the set Y, so that that ordered pair is in the relation. Relation being that subset we defined up there for a Cartesian product. Each input gets at most one output. Names you've all heard before: domain, codomain, range. You start in the domain, you end in the codomain. The things you actually hit are the range of your function. Now, when we talk about sets being finite or infinite, we're talking about cardinality, right? We had countable infinite, we had uncountable infinite, right? How did we figure out whether sets have the same size? What does it mean for a set to be finite?
There's only so many options for it, like you can't just keep going and going.
Okay, so I would say there's some number, and when I reach that number, I've run out of things, right?
Yeah.
So S is finite. If it has some number of things in it. S1, S2, up to Sn. It's a finite list. It could be a huge list, right? The books in the Library of Congress is a finite set. It's just gargantuan. So what's it mean to be infinite?
It's like infinitely many elements.
Yeah, that's a recursive definition. You can't use the word in the definition.
There's a non-ending amount of elements.
I'm just going to say I can't do that. How about we just say it's not finite?
I think that's still technically like using.
So we define something by saying what it isn't, right? Books that refer to themselves, books that don't refer to themselves. So you're not in this group, you must be in this group. In one way it is using the word, but I'm not using infinite in my definition to describe infinite. I'm making my definition a circle. I am using finite, but I'm not using infinite. Does that help, Jim, or does that hurt?
I was just trying to be like, it's not in.
Well, right. I understand that. But in this case, I'm trying to use the idea of what it means to be finite to define not finite. We're just going to make it one word. If it's not finite, how do I count it? If I have an infinite set, how do I count it? Or even if it's finite, that's what I'm counting, right? 1, 2, 3, 4, 5, 6. These are the things. 1, 2, 3, 4, 5, 6, 7. Done. I ran out of students in the room. But if it's infinite, I'll be here forever. That's kind of not helpful, right? I think it's infinite. I'll start counting and see. If I die before I'm done, then it was infinite. No, it just lasted longer than you did. But this idea of counting is actually a function. When I counted you all in the room, I made a function between the set 1 through 7 and you. And not just any function. All right, what do those two terms mean? A one-to-one function and an on-to function. Please.
One-to-one means like every value has its own like respective like answer at like a better word, and on-to means that every value hit.
On-to means I hit all of it. One-to-one means I only hit each thing once. X squared is not one-to-one because both 2 and -2 hit 4. It's not onto because nothing hits -2. But I went from the set of numbers 1 through 7 to you all. And I could do that in a lot of different ways, but anytime I do, if I can do it in a one-to-one and onto function, then I have decided the size of this set is 7. Two sets have the same size if I can build a function between them. It's one-to-one and onto. And that goes for finite sets and infinite sets. What's my ideal first infinite set? Well, it's a set of counting numbers where I just never stop counting, right? So the natural numbers is infinite. So I'm going to give this infinity a name. We're going to call the size of the natural numbers a name. That's Aleph, the first letter in the Hebrew alphabet from which we get alpha, and therefore alphabet. Those are the first two letters, Aleph, bet. Aleph 0, Aleph null, or Aleph sub-0. There are all those terms. That's countable, because I'm typing infinite set. And that's sometimes referred to as countable infinity. But that means if I want to know if a set is countably infinite, I should try and connect it to this one with some one-to-one and onto function. So, Ian, you said earlier this set is bigger, right? I claim it's the same size. I claim this set, the integers, is the same size as the natural numbers. Dr. Sassmore, are you stoned? No, I promise. This really works.
Is that where Cantor did his proof or Garrett?
No, we're not even there yet.
Okay.
We're way before that. You can go in either direction. If the function is 1 to 1 and onto, then I can go from set A to set B, or from set B to set A, simply by turning the arrows around. Because everything only hits one thing and everything got hit. So there has to be a direct, exact match between my two sets. So I'm going to do this, in my opinion, in what I consider to be a visually easy way. Here is the set of natural numbers. And I included 0. And now what I'm going to do is I'm going to write down all the integers in a way that I hope you can extrapolate the pattern. I'm going to start with 0. And now you have a choice. Do you want to go to 1 or minus 1? 1. Well, then I'm going to go to minus 1. And then I'm going to go to 2, and then I'm going to go to minus 2. Then I'm going to go to 3, and then minus 3, and 4, and minus 4, and 5, and what would be next? And I would just keep going out. But because you went 1 first, I go right, then left, then right, then left, then right, then left. Am I going to be able to match up everything? Am I going to exhaust all of the integers if I continue this list forever? Then there's a 1 to 1 and onto connection here. These sets must actually be the same size. There's my function, phi, from the top set to the bottom set. Now, people started getting pissy about this and said, well, let's look at an even bigger set. Let's look at the set of all fractions. There are way more fractions than there are integers, right? And somebody went, no. I can count them the same way. Bullshit. How do you count those? Start with 0. Then I'm going to write down all the fractions, but instead of them writing them in a line, I'm going to write them in a grid. And I'm going to write the fractions in each row based on their denominator, and in each column based on their numerator. Actually, I just said that one way, and I'm doing it the other way. The rows are the numerators, the columns are the denominators. Sorry about that. And the game is now, how do I put them in order? How do I straighten this out to be a line so that it matches up with one of those lines above? And the answer is diagonally. But you skip any number you've already run into. So here is 0. That's my first number. Do you want to go right or down? Your choice. Down? Well, that gives me 1. That's my second number. Now I go diagonally, but I've already seen that number. Skip it. Move over to the next diagonal. I've seen that number. Skip it. Go this way. That's the third number. Go this way. That's the fourth number. Fifth. Oh, that's 1 again, right? Skip it. 1/3, that's a new number. That's 0 again. Skip it. Skip it. New number. New number. New number. And eventually I will unfold that entire grid. And this fraction set must also be countable. And people got pissed off and said, damn it, everything's countable. Along comes George Cannon. And he says, no. I want you to look at the numbers between 0 and 1. Not including 0, not including 1. And he says every number in this set is a decimal that starts 0 point stuff, right? So I'm going to say we have digit number 1 and digit number 2 and digit number 3 and digit number 4. And the number keeps going. There's only one rule. You cannot have an infinite end of 9s. If you have an infinite end of 9s, you round up. There's a limit procedure there, and that's why 0.99999 is equal to 1. He said, so here's what you do. You're going to make the list. You're going to say, we have a number in here. Real number 1 is going to have the first digits. 1, 1, 1, 2, 1, 3, 1, 4. And then the second number is going to have 2, 1, 2, 2, 2, 3, 2, 4 as its digits, right? The third one will be 0.D31, D32, D33, D34, and so on. And George says, I'm going to build a new number. The new number has one rule. Its first digit is not this. Its second digit is not this. Its third digit is not this. I make this new number. Is it on your list? Its 175th number is different from R175. It can't be on the list. No matter what number you pick off, you missed it. If this is your function, the first number, the second number, the third number, you missed one. No matter what you picked to fill in this list, you missed one. This set is uncountable. And it turns out that this is now a new size of infinity. It's bigger. And he called it the continuum. It's a funky looking angular C. And it turns out that there are lots and lots and lots of sets that are this size. There are lots and lots of other infinities also. And finding the ordering of those infinities is hard. It turns out to be an unsolvable problem. We can't prove one way or the other. We either accept that there are other infinities or deny that there are other infinities. And the whole consequences of math change when we pick which rule, which version of the game we want to follow. It works out a lot better, and there are a lot more interesting results when we accept it than there are when we deny it. That's called the axiom of choice. Because Cantor's argument said I have to be able to make an infinite number of choices at once. I have to choose all those digits. Be different. One felt sweet. And there are people who say you can't do that. That doesn't make sense. Any procedure has to run in time. No, I want to be able to do it all in one move. That's a philosophical argument rather than a mathematical one.
This might not be related to it, but would that be something that like a quantum computer, for example, might be able to handle all the time?
We have absolutely no idea how a quantum computer is going to work.
Right.
It does stuff we have no idea what's going on in it.
Okay, so no.
Yeah, my quantum computing setup is absolutely differentiated from the axiom of choice. This, by the way, this argument's on page 6. But you also saw it in chapter 2, section 5 in the discrete book. Even if you hated it back then, this is the last time you're going to see it. Okay. Cantor's actual book is about, well, the direct version of his paper is only about 45, 50 pages. So it's a really, really dense argument on Cantor's. Okay. One more thing about sets that I really want to talk about are partitions. A partition is a way of breaking up a set. A partition of a set S is a collection of disjoint, non-empty subsets of S whose union is all of S. Excuse me, what the? That's a set of words, and mostly English words. What the hell does that mean? Well, really it means there are three conditions. Each of the individual sets is not empty. Any two sets have no overlap between them. And if you took all of them, glommed them all together, you get all of S. Now this sounds kind of dumb, but you've done this a lot. We did it with our books earlier. Books that do refer to themselves, books that don't refer to themselves. You can't have both, except for a weird idea. So if we wrote with real legitimate books that are already in the Library of Congress, not this new one I'm making, then that's the two-set partition. We do this in numbers. Let's look at the natural numbers, or even the integers. I'm going to partition this into any number of sets you want. Somebody give me a number. 4. Okay. Now I can do this in a whole bunch of different ways. Here's what may sound like a dumb one, but I'm gonna run with it here. Is it clear to you that every integer, whether positive or negative, is in one of those 4 sets? Is there any overlap between any of those sets? And if we go on them all together, we're going to get all of the integers. None of them are empty. That's a partition. I could have done it in 2 sets, right? Even, odd. Here I did positive even, negative even, well, non-negative even, negative even, positive odd, negative odd. That works. One you've seen before. This is my first set. It's all the multiples of 4. Right? Here's my next set. What are all the numbers in there?
Added by 4, subtracted by 4.
From where?
1.
Aha! So all of those numbers are 1 bigger than a multiple of 4. I can do 2 bigger. I can do 3 bigger. So here are 4 sets. Multiples of 4, 1 bigger than a multiple of 4, 2 bigger than a multiple of 4, 3 bigger than a multiple of 4. Or, another way to think of these same sets, take your number, divide by 4, and tell me what the remainder is. You're in this first set if your remainder is 0. You're in the second set if your remainder is 1. The third set if your remainder is 2. And the fourth set if your remainder is 3. We called these residue classes. And then we were mod 4 or modulo 4. These are remainders. By the way, I can do any number. I'm glad you picked 4. It was nice and small and easy to write out. Somebody said 17 a couple years ago. I said no, something smaller. Now, here's something interesting. Those 4 sets and the other set of 4 sets define a relationship on the set of numbers. 2 things are related if they're in the same set in my partition. Every partition creates a relation, not just any relation, a relation that has properties, a relation that is reflexive, that is symmetric, and that is transitive. And that's called an equivalence relation. Reflexive means that everything is related to itself. Symmetric means that if A is related to B, then B is related to A. Transitive means if I go from A to B and B to C, I can go from A to C. Partitions make equivalence relations, and equivalence relations make partitions. Chapter 9, Section 5 in the Street Book. We did this before. And now I really want to say that's the start of this semester in general. We're digging back into the street. Where am I going to go from here? I'm going to start looking at examples of the simplest kinds of structures we can make from sets with operations. Like doing one move after the other. And that's what we'll do on Thursday. Okay, well, have a wonderful rest of your day. I will see you all then.
So, sections here.